without me. You can be honest. It was fine. Okay. Well, I want to start by giving you guys an opportunity to take some questions. So if you guys have questions about anything, whether it's homework or if it's content or whatever, I'm happy to spend a few minutes now taking care of that. Abby? Yeah, we can. So it's 38 is mostly just kind of a big pain in the butt, but that's okay. But it's not so bad. So basically what I'm going to do is I'm going to take those three vectors, or those three sides of our triangle, and represent them as vectors. So I have xy, I have yz, and then I have like zx. Okay, and I'm going to represent them in component form. So that's going to be the tail, which in this case would be y, minus the head, which in this case would be x, and then y minus x. And then here we're going to do, again, tail minus head. So z is the tail, so 5 minus negative 8. And then 7 minus a negative 4. And then zx is, x is the tail, so negative 2 minus 5, 1 minus 7. Now, in addition, I may end up needing the reverse of each of these. Now, I don't really need to solve the component form for each of these because it's just going to be the opposite direction. So I can just flip the signs on the x and y coordinates to get those. I'm not sure I'm going to need those, but I'm going to write them down right away here. So the side lengths are easy to get. We can just kind of do that magnitude formula because the magnitude of the vector is going to be the same as the side length if the vector is representing one side of our triangle. So let's see, 36 and 25 is 61. And then yz is 13 plus 11. What's 169 plus 121 is 290, I think. And then zx is my last one. So 49 plus 36 is 85, I think. So those are my side lengths. Cool so far? Okay. Now if I want the angle between, or the angles, the interior angles, if I think about my triangle here, so like x, y, z, obviously this isn't to scale, I didn't put anything anywhere. If I want angle x, I need the vector xz and the vector xy, right? Will get me this angle x. Okay with that plan? So I'm going to use the angle between two vectors formula, which we covered in the notes last time. So that says theta is cosine inverse of u dot v over the magnitude of u times the magnitude of v. That's the formula. So in this case, if I want the angle like y, x, z, that's going to be cosine inverse of xy dot xz over the magnitude of xy times the magnitude of xz. So xy is -6, -5. And then xz is 7, 6. So 7 times -6 is -42, plus 6 times -5 is -30. So that's -72, I think, right? 42 and 30, yeah. And then the magnitude for xy is the square root of 61. Oops. Forgot that cosine inverse there. And then the magnitude for xz is the square root of 85. If I go and I type that into my calculator, that'll spit out my value. Let's do it that way. So when I do that, that's about 179.20 degrees, which seems a little suspicious, but if you actually graph these 3 points, it's almost a straight line. So maybe not so surprising that the obtuse angle is close to 180 degrees if it almost looks like a straight line when you graph it. And then to find the other angles, y and z, you just kind of use that same formula over again. It's a little tedious. Can I stop there, though? Okay. I feel like that was enough to kind of round it out. Or that you could, go the rest of the way yourself, since there's not much to do other than like the same thing over again 2 more times. Just be careful that you're using the right 2 angles when you, or the right 2 vectors when you're finding the angle. The key is that you have to have both of the, the tail of the vector has to be at the angle you're looking for. So if you wanted angle z, you need zx and zy. You know what I mean? That's the only place where really you have to be kind of careful. So I probably did need to include find all 6 of those vectors that I wrote down there, because it's hard to tell right away which one you're going to want, xz or zx, and you're very likely going to need the other direction when you find the other angle. When you go look, like if we'll go look for angle z, I'm going to need zx then instead of just xz. So I think I will need all of those. Ben? Of course, yeah. Again, if you ever have trouble seeing with the lights on or whatever, stand up and turn them off. Don't wait to ask if you're having trouble reading anything. Yeah, you're welcome. Victoria, you had your hand up earlier, did you not?
Yeah, I did it. I figured it
Oh,
out.
okay. No problem.
Thank you.
Yeah, of course. Others from questions, again, could be from homework, could be just in general. I know I was gone for the last lesson. I left you a video that was basically the video of 4th hour's lecture, so it should have been rather complete, but I know sometimes watching a video and sitting in class and actually hearing it is sometimes 2 different experiences. So I just wanted to make sure I make time for that if there's anything that you're still unsure about. But again, this hopefully was fairly easy to understand what we were doing, since you're just kind of doing some new operations, right? There wasn't anything, I think, tremendously complicated that we dealt with there. It was very much, all would have been new, right? These are probably new vector operations you've never experienced before, but the actual calculations involved were nothing really sneaky going on. You know what I mean? Okay. So that being said, let's move on and start talking here about the next section, 8.3. So when we talk about applications of vectors, we're going to be looking at basically two different kinds of applications. Now, the first application we're already kind of familiar with because this is the same kind of problem we dealt with in, I think, in like chapter 4 when we talked about bearing problems. You remember doing those bearing storing problems in first semester? Maybe, maybe not. Let's just do an example here. But we'll do this same bearing problem this time using vectors instead of right triangles. And I think makes it perhaps, it's very similar still, but and again, I think when I did this first semester, I did it more like a vector problem already than a triangle story problem. So if you had me first semester, this should feel pretty familiar still. All right, so it says a boat leaves a port and averages 40 knots, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? So when I read this, there's basically two legs of my journey. The first one is 40 knots for 2 hours at 215 degrees. And the second leg is 55 knots for 3 hours at 162 degrees. And what I'm going to do is I'm going to start by converting these into vectors. So first thing first is that I need to convert these bearings into standard position angles. So I find the easiest way to do that is to draw a picture because so remember that a bearing and a standard position angle are found two different ways. A bearing starts at true north and rotates clockwise. So 215 degrees is like, I swear I changed the color. Starts at true north and then we go clockwise, so that's 90, 180, and then like 35 more would get us to 215. Now the standard position angle starts at the positive x-axis and rotates counterclockwise. So that's going to be 90, 90, and then this part here is going to be the complement of 35. So that's 55 degrees. So here my standard position angle is going to be 90 plus 90 plus 55, so 235. And then the other one, the bearing is 162, so 90, and then like 72 more. And the standard position angle, though, is going to be going this way. So 90, 90, 90, and then the complement of 72 is 18. So 90 plus 90 plus 90 plus 18 is 288. Again, you don't necessarily have to draw the pictures to do this, but I find that like it's almost impossible for me to screw up that conversion if I draw a picture. So that's just the way I like to do it. If you want to do it like algebraically in your head, that's fine too. Like this is just the way that I like to do it because I would prefer not to have to think about it that hard. If I draw the picture, it's just fairly intuitive how to do that, at least to me. You know what I mean? I'd rather not have to like memorize more formulas. It's just like, okay, I'll just draw a little picture and figure it out. You know what I mean? Okay. This is the directions now for my vectors. The magnitude for my vectors, I'm going to find by just taking is going to basically be the same thing as the distance, like how long was that leg. So 40 knots for 2 hours gives you 80 nautical miles. And 55 knots for 3 hours gives you 165 nautical miles. And now I'm going to just convert these, translate these vectors into component form. So that's 80 times cosine 235 and 80 times sine 235. For the first leg, I'll call that vector L1. And for the second leg, I'm calling that vector L2. That's 165 cosine 288, comma 165 sine 288. And then the actual vector, the actual displacement from the port to where we started, is just going to be the sum of those two vectors. So when I do 80 cosine 235 plus 165 cosine 288, I get about 5.10. When I do 80 sine 235 plus 165 sine 288, I get negative 222.46. So I just typed those into my calculators where that number came from, right? I just added the x component and the y component together. I just didn't want to have to write it down a second. You know what I mean? You guys get it. You know how to do vector addition. Yes, we're okay? So to find the displacement, I can then now just find the magnitude of that resultant vector, which is about 222.51 nautical miles. And then to find the direction, again, I like to draw a picture to kind of supplement this because sometimes I think without a picture it's easy to make a mistake in forgetting, like, do I need the complement or the supplement of this? Should I be adding 360 or subtracting it or adding or whatever? So the easiest thing to do is to A. So if I plot A, I'm going 5 over and negative 200 down. So that's A. The bearing for A, which is what it asked for, is this. So that bearing is going to be 90 plus whatever that angle is there, which I'm going to call phi, is the variable name I'm going to give it. To calculate that angle phi, an inverse of the y component from A over the x component from A, but I'm going to take the absolute value of those. So when I do that, I get about 88.69. So my bearing is going to be plus 8.69 or 178.69 degrees. Yes, Sophia.
How did you get the further up? How did you get the nautical miles? Like was it given in the problem?
Oh, this is 2 times 40, 3 times 55.
It's just like by the hours.
So the magnitude is the same thing as the length of that vector,
Okay.
which is just like the distance on that leg of the trip. So it's just going to be a distance in that case. Yeah. At least if it's a navigation problem, it'll just be a distance. Okay. Ben.
What numbers do you put into the
So that's the y component of A over the x component of A. So that would be negative 222.46 and then 5.10, but I'm taking the absolute value of each of those. So just the positive of them.
I actually put it as 5.13.
Oh, yep. That would explain why you got like an absurdly small angle, right?
I got like
Yeah. Yeah, you got this complement of that, like 1.31 or whatever, yeah. Yep. No problem. So remember just like the definition of tangent, y over x. Yep. Yeah, it's an easy one to get to goof. But again, when you draw the picture, you should know immediately like, yo, 1 degree is not right. So that helps. Again, the picture I think really makes it easier to kind of catch those mistakes if you draw that and you're like, 1 degree isn't right. What did I find? And in fact, really, Ben, you would have found this angle right there, which again, you could have made work. You could have then done 180 minus that, and you would have gotten the same result. Yeah, no problem. Okay. So the next idea here that we want to talk about is ways to break up a vector into orthogonal components. And this is something that we did kind of in a trivial way last time, right? You know, for example, if we had the vector 3, 4, we could break that up into the vector 3, 0, right? Now those two vectors are going to meet at a 90-degree angle, which is what we mean by orthogonal. Everybody's okay with that idea? And that's trivially easy to do, right? You just put everything in the x direction that's in the x direction and with the 0 y, and then a 0 in the x direction with everything that's in the y. But what if we want the orthogonal component, one of the orthogonal components to be in the same direction as another vector? So what we're talking about is, say we have this vector u. Hi, how's it going?
Okay, so yesterday, I had no idea that the fax machine didn't make noise anymore.
Yeah, I talked to brother.
It would have gone through.
It would have. Yeah, I figured.
I had no idea.
Well, now we
Live
know.
and learn, right?
Yep. Victoria, you have a get out of jail free card here. You're welcome. So we have this vector, let's say we have this vector u that we want to break into two orthogonal components, okay? But instead of wanting orthogonal components, let's say that one of them we want to be in the same direction as v. So there's a vector v. We want one of its orthogonal components to be in v, in that same direction of v. So really what we want here is we want to find these two vectors here, right? Everybody's okay with that idea? Those two would be orthogonal. And clearly, from the picture we've drawn, they would add up to give us u because of the head to tail part, right? So far, so good? Okay. This vector here, we give a name to. We call this vector the projection of vector u. So really, all this projection vector is a scaling of vector v, right? It's the same direction as v, it's just different length. Everybody's okay with that idea? So all we need to do is multiply vector v by some scalar, and that'll give us this projection vector. Everybody's okay with that notion? Now, what that scalar is not obvious at a glance, but we do have a formula to calculate it. Tell you. Okay. So the way dot product of vectors u and v divided by the magnitude of v squared and then we still have to multiply it by vector v, because the scalar is just u dot v over magnitude of v squared. This other vector I'm going to call w, the other orthogonal component to u. Say three things about this projection. So the first thing we can say is that the vector u is equal to the projection of vector u onto v plus that vector w, where the projection and that vector w are orthogonal. Again, orthogonal just means they meet at a 90-degree angle. So the second point I want to make here about the projection is I want to go back and refer to this picture that we drew initially. Now, when I drew this picture, did the length of vector v really come into play here? Did v have to be longer than the projection in order to draw this picture? Not really, right? Could it have been shorter? You know, could v have been this? And still would I have been able to draw that same picture? Yeah. Really, all I needed from V is the direction. Everybody kind of agree with that? So in a strictly abstract sense, the length or the magnitude of V doesn't really matter to us. All we really need is the direction. So in a case where we're not told really information that would imply the length of V, it means we have the freedom to choose V to be any length. What length do you suppose would be a good length to choose for V? 1. And we'll look at, in the following examples, situations where we can make the assumption that the magnitude of V is 1, and a case where we cannot. And I'll point out to you like the way or the information that is given in one problem that's missing from the other. So here's just like a strictly numeric example. So in this, we're asked to do two things. We're asked to first find the projection of U onto V, and then to express U as the sum of two orthogonal components, one of which is the projection of U onto V. So the first thing I'm going to need to do is to calculate that projection. So my formula is UD for the magnitude of V squared times vector V. So let's do the dot product. So the dot product, we multiply the x's and we multiply the y's and then we add them together. So 18 plus -4 is 14. The magnitude of V squared is going to be 6 squared plus -4 squared, square rooted, but then squared. So 36 and 16 is 52. Everybody so far so good? Ben? 6, it's in parentheses. Make that a little bigger, probably easier to read that way. So when we plug this into our formula, I have 14 over 52 times 6 negative 4. Now, 14 over 52 reduces, right? So I'm going to do that. I wrote it first as 14 over 52, though, so if you're going back and looking at your notes, you're not confused as to, like, how the heck did he get 7 over 26? There's not even a 7 or a 26 anywhere in this problem. So I intentionally wrote it first as 14 over 52 and then did the reducing so that hopefully it's less confusing if you go back to look at this later. Everybody's okay there? Okay. And then we'll multiply, do that scalar multiplication. So 6 times 7 is 42 over 26. And then 7 times negative 4 is negative 28 over 26. And again, these both reduce. I could have reduced before I multiplied, which is really what I would probably do in practice. But again, I don't want it to be confusing, so I'm going to do the obvious multiplication and then reduce afterwards. So it's, again, not unclear as to what the heck I did if you go back and look at these notes. So there's my answer for part 1. There's the projection. Everybody so far so good? Now for part 2, what I'm going to use is the fact that I know that u is equal to the projection of v onto u plus that other vector w. Since I know what u is, and I know what the projection of v onto u is, I can just do algebra here to find w. Everybody's okay there? I just subtracted that or the projection vector from both sides. So when I make a common denominator, 3 becomes 39 over 13. 21 minus 39 is 18, so I have 18 over 13. 1 becomes 13 over 13. 13 plus 14 is 27 over 13. And that's w. So I can say then u is 21 over 13, comma, negative 14 over 13, plus 18 over 13, comma, 27 over 13. And that's my answer for part 2 then. Okay. Does that feel okay? Nothing too tricky there, right? At least from a computational standpoint. Let's do some story problem examples to kind of show you how we can incorporate this idea of a vector projection into a story problem situation and what that's going to sound like. Ben.
How did you get the orientation?
just did the scalar multiplication. Yep. Okay. Make those words a little bigger so that you guys can actually read them. All right. So some story problem examples here involving these vector projections. So Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what is the amount of force, or what amount of force is sliding down the hill? So I like to start by drawing myself a picture. And in my picture, I'm going to involve two vectors. So the first vector I'm going to draw is Kyle and the sled weigh 165 pounds. So what force creates weight? Gravity, right? If there's no gravity, there's no weight. Everybody agree with that? What direction does the force of gravity act? Directly down. So this is what I'll call my vector G. And that vector G is obviously then the component form 0, negative 165. Is everybody okay with that? For obvious reasons, right? Everybody's okay with how I got the component form there, just trivially from drawing the picture? Okay. The other vector that I'm going to draw is this hill, because that's what we're projecting the force due to gravity onto. So that says the hill, we're sledding down the hill, and the angle of incline is 25 degrees. So there's my hill. My angle of incline would be this angle here, but from alternate interior angles, I know that that angle is also 25 then. Is everybody so far so good? Okay. I'm going to call that vector vector H. So what can we say about this vector? Well, do we know anything about the length of the hill? Does it matter? Not really. We can assume it to be 1. What's the direction? It would be that, right? So 360 minus 25 is 335. Write it that way first. So if I resolve then vector H into component form, I have 1 times the cosine of 335, and then 1 times the sine of 335. Everybody okay there? The question that we're asked to answer now is the amount of force sliding down the hill. That's going to be the magnitude of the vector that's the projection of the gravity onto the hill. So we're going to calculate that projection vector and then find its magnitude. And that should be the answer to our question. Is that okay? So the projection of G onto H is going to be G dot H over the magnitude of H squared times the vector H. Well, 0 times 1 cosine 335 is 0, and then plus negative 165 times 1 sine negative, or sine 335 is just negative 165 sine 335. And the magnitude there is 1. And there's my vector v. And when I do that scalar multiplication, I get about 63.20, negative 29.47. And then if I do find the magnitude of that vector then, that's about 69.70 lbs. Oops, 73. Questions so far on what we've done? Okay. We do one more example and we'll be done for the day. Okay. The next section is quite lengthy and I don't want to get into it with just a little bit of time today. And this one, again, these story problems are, well, not so difficult. They're certainly have some additional like soft math skill built in, that like reading and understanding the situation is going to be a little bit of a challenge on top of the new techniques that we've learned today. So I don't want to overdo it today because this can be a frustrating section if you have trouble reading and understanding story problems. So I don't want to add on too much extra stuff right now or right this second. You know what I mean, guys? So one more example to contrast with the other one. Those of you that are any of you guys in a physics class right now? A couple of us. These sound relatively familiar, these problems that we're looking at right now, where you have forces involved at an angle. Those were always problems that I had a hard time with as a physics student because they do so many tricks to like tilting the axes and stuff, that just to get away with not having to deal with as many vector things. And I find this method so much easier because it's really the exact same thing every single time. There's no tricks that you have to remember. But maybe you're a better physics student than I was. All right, the next question here, we have a crate that's being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. So that's one force vector, or one vector. So that's the vector that's how the crate is being moved. Second vector, it says the ramp measures 10 feet horizontally and 2 feet vertically. That's my second vector. Assuming the crate is of negligible weight, what is the amount of force directed up the ramp? So let's draw a little picture here to represent that. And in this case, you probably don't even really need the picture because I think from the wording it's relatively clear. So I'm going to draw the ramp first because the crate is sitting on the ramp already. So we go 10 feet horizontally and 2 feet vertically. So there's like my ramp. And clearly that would be component form 10-2, right? Since we went 10 horizontally and 2 vertically. Right away, what can we say about this vector here? Does this have a length associated with it? Yes. So here's a situation where I can't just assume that the magnitude of this thing is 1. Everybody's okay with that? Now, if you wanted to, you could convert it into a unit vector in the same direction. But I feel like that's no less work than just finding the magnitude of v and putting that into the formula, which is what I would suggest you do. But if you wanted to do that, you could. I think it's not really worth your time. And then my other force vector for the crate says an angle of elevation of 40 degrees. And the force is 100 pounds. So C is going to be 100 cosine 40, 100 sine 40. Everybody's okay with that idea? Now that I have my two vectors both in component form, I can calculate the projection vector, since again, if we want the amount of force directed up the ramp, that is talking about the magnitude of the projection of C onto R. So C dot R is going to be 10 times 100, which is 1,000, and then cosine 40, and 2 times 100, which is 200 sine 40, over the square root of 10 squared plus 2 squared square rooted squared. So that's just going to be 104 times the vector 10, 2. And when I type all that gobbledygook in my calculator, I get about 86.02, 17.20. But I'm not done because I don't care about the vector, the projection vector. I really care about its magnitude. So the last step there is just to calculate the magnitude then. What do you guys think? Again, the most difficult part is usually just interpreting what's going on, in the making sure you can translate the words into the correct vectors in the right positions with the right components and all that. Once you get the vectors, though, the vector projection calculation is not terribly difficult. Really, you're just plugging things into a formula. And then it's usually fairly rote from there. The tricky part is usually the beginning step where you make sure you have the problem set up correctly from the words. You know what I mean? I'm going to stop here. Like I said before, this is going to conclude this section 10.3, and the next section 10.4 I think is complicated enough that I don't want to get into it today and have to start midway through, as it's not a there's not a natural break point in that section that I would want to stop at. In addition, these story problems are often not trivial for students, especially in the beginning, so I don't want to overload right here. So for Sunday's homework check, I'd like you to do, in addition to the previously assigned problems, 41 to 50. So 4 of those are just like calculate this projection. Just like use the formula, here's some numbers. And the other 6 problems are story problems. Okay, so that's that.